Energy analysis is an alternative to an analysis using forces. And it's similar to accounting, where energy flows like a currency between different parts of the system and in different forms. Work is one method of transferring or transforming energy. Forces can do work on an object to move it. Here's a boulder with a force applied to it. That force causes that boulder to move, and it moved by a certain amount called the displacement. Work is a gauge for how much effort a force does to displace an object. So it makes sense that a larger force will do more work, and a force that displaces an object by more distance will also do more work. And so the work done will be a product of these two. However, not all of the force can displace an object, and so not all of the force can contribute to the work. In the diagram shown here, an upward pulling force can be broken up into two parts, a parallel part and a perpendicular part. The parallel part is what's responsible for displacing this object on the horizontal axis. The perpendicular component of the force doesn't lift the object up, and so there's no vertical displacement, and so the vertical component of the force does not do any work. Let's look at the SI units of work, energy, and power. Because work is the transfer of energy, it'll have the same units as energy. So we'll just look at work. Work is force multiplied by displacement. We know that force is measured in newtons and displacement is measured in meters, so work must have units of newtons times meters. And we call that product a joule, or capital J for short. In terms of the SI basis units, we can replace a newton with its SI basis units of kilogram meter per second squared, multiply that by meter to get kilogram meter squared per second squared. Power is the rate at which work is done, and rate is a word which means you take that quantity and you divide it by the time interval. So power is just work divided by the time interval that took for that work to happen. Well, we know that work is measured in joules and time is measured in seconds, so power is measured in joules per second, and we call that quotient a watt, or a capital W for short. In terms of the SI basis units, we can replace a joule with what we have on the left-hand side and divide it by a second to get a watt is a kilogram meter squared per seconds cubed. Let's look at an example of a simple machine. Here, force 1 is applied to the left-hand side of a lever, which does work to lift a heavy object on the other side. If the objects here are rigid and the system is isolated, then the work done by force 1 will be equal to the work done by force 2. We know that work is force multiplied by displacement, so we can use that to solve for the amount of force that can be applied on the right-hand side of the lever, which is just the ratio of the displacements multiplied by the first force. Here's an example using numbers. If the downward force F1 is 54 newtons, and it pushes downward by a distance of 92 centimeters and lifts a heavy object 31 centimeters, what's the force, or how much weight can be lifted? Well, we calculate force 2, which is the ratio 92 centimeters divided by 31 centimeters, multiplied by 54 newtons, and we get 160 newtons. You should note that all of these quantities have two significant figures. Here are some things to think about. Why does the lever have to be rigid? why did the system need to be isolated for the previous analysis to be true? If the lever's length was fixed and the downward force was constant, how could the system be modified to increase or decrease the amount of weight is lifted? Let's look at an example of work done against friction. In this case, a block is pushed with constant velocity along a surface with friction. Because it's moving with constant velocity, its acceleration is zero, and the pushing force balances the kinetic friction. So the net force is zero. When the block travels a distance d, we can still calculate the work done by each of the individual forces. So we multiply the net force by the displacement d, and we get the work done by the pushing force and the work done by kinetic friction. Now the work done by the pushing force puts energy into the block to move it. The work done by kinetic friction takes that energy out of the block to slow it down. And these two forces perfectly balance each other so that the block moves with zero acceleration. If, on the other hand, the pushing force is significantly larger than the amount of friction, then there will be a net force. This net force does work on the block to increase its speed. Let's now look at the work-kinetic energy theorem. As shown on the previous slide, work can change an object's motion. That is to say, work can change an object's speed. Energy associated with motion is called kinetic energy, or Ke for short. The work-kinetic energy theorem says that the net work done on an object is equal to the change in that object's kinetic energy. Kinetic energy exists in two forms. One is translational motion. This is motion on a line. Then there's rotational motion. This is where an object rotates around a pivot point. Some objects will have both. For instance, the wheel of a car or a ball rolling down a hill. In these cases, the object rotates around a central axis and it moves. In this class, we'll focus on translational motion. And the kinetic energy associated with translational motion is equal to 1/2 of the object's mass multiplied by its speed squared. It's important to note that if the object's mass doubles, the kinetic energy will also double. But if its speed doubles, the kinetic energy will increase by a factor of 4. Let's look at the work done by gravity in 3 scenarios. First, a crystal falling. Second, a block sliding down an incline without friction. And finally, a ball tethered to a rope that falls through a circular arc. All 3 objects fall through the same height and have the same mass. How much work does gravity do in each case? Because the mass is the same for all objects, the weight is also the same for all of them. Gravity points exactly downward. It never points in any horizontal direction. It only goes straight down. Because of that, gravity is parallel to the displacement, delta y. The work done by gravity is the mass multiplied by the acceleration of gravity multiplied by delta y. We can rewrite this to pull the delta sign out, and we say that the work is negative the change in the mass multiplied by the acceleration of gravity multiplied by the y component. We say that that quantity in parentheses, mgy, is called the potential energy due to gravity, and it is the amount of energy stored in that object due to its location above the ground. The change in the potential energy due to gravity depends only on the change in the vertical displacement and not on the path taken. Because of that, gravity is said to be a conservative force. In the previous slide, we saw how to calculate the potential energy. And we found that the potential energy due to gravity is equal to the object's mass multiplied by the acceleration of gravity multiplied by its position above the ground. Potential energy is energy that is stored in a system and depends on how the components of the system are organized. Or in other words, how the system is configured. When the system's potential energy is released, work can be done to change the motion of the system. And it exists in several common forms that we'll look at next. Let's look at several different forms of potential energy. We already saw in the previous slides that energy can be stored by placing a heavy object high above the Earth's surface. This is called potential energy due to gravity. One example is a water tower, in which water is stored in a vessel high above the ground. The water can be released and allowed to flow through a generator, producing electricity. Gravity is also what holds our planets and a solar system together. A spring can be stretched or compressed, storing energy. And the image on the left is a linear spring, and the image on the right is a torsional spring. An electric field can also be used to store energy, and devices that do this are called capacitors. A capacitor works by having two conductive plates separated by insulating material, also called a dielectric. When a voltage applied across the dielectric, an electric field is built up and energy is stored there. These devices are often placed next to integrated circuits to supply a small amount of energy in case there is a drop in power. When electrons flow in a conductor, they generate a magnetic field. A piece of copper can be wound up into a tight coil with a piece of iron in the middle. This device is used to store magnetic energy and is called an inductor. A battery is a device which separates two groups of chemicals, one at the anode, one at the cathode. When a conductor is placed between them, a set of redox reactions are allowed to occur, and electrons can flow through the conductor. The example here is a lithium-ion battery cell. Breaking chemical bonds is a very common technique to get energy. For example, burning wax, burning coal, or petroleum, or breaking the bonds in a hydrocarbon molecule. Breaking those bonds produces energy and releases carbon dioxide and water. Biological systems get energy by breaking a bond in adenosine triphosphate. This molecule is an adenine nucleotide bonded to a ribose, which is then bonded to a line of 3 inorganic phosphates called alpha, beta, and gamma. When an enzyme needs to do some sort of work, it will break the gamma inorganic phosphate molecule. This releases energy to do some sort of work. For example, the sodium-potassium pump will hydrolyze ATP, which will then pump out 3 sodium ions out of the cell. Mass can also be converted into energy. This is how nuclear reactors work. They break up uranium atoms, which will then release energy. Another example is when a positron and an electron collide to annihilate each other. A positron is the anti-electron. It has the same mass, the same amount of charge, but just the opposite sign. When they annihilate each other, all that mass goes away and 2 photons are released. The amount of energy is E equals mc squared. Now let's revisit the work done by friction in 2 different cases. In the first case, a block is pulled along the surface with friction, and it's pulled in a long, windy path. In the second case, the block will be pulled from the same starting point to the same ending point, but this time a direct path. So the question is, was the work done by friction the same in both cases? To answer this, we'll first note that friction is always anti-parallel to the motion. That is to say, it's in the same direction, but exactly backwards. The work due to friction is going to be equal to the amount of friction multiplied by the displacement. But because the displacement is always backwards from the friction, the total displacement is just going to be the total length of the path. And so the work is equal to negative amount of friction multiplied by the path length. So the longer the path, the more work is done by friction. The negative sign means that energy is taken out of the system. So in case 1, more work was done because the path was longer than in that of case 2. The lesson here, work due to friction depends on the path taken, which is different from that of the potential energy due to gravity, where the work done only depended on the starting and ending locations. It did not matter which path was taken. These kinds of forces, where the work done depends on the path, are called non-conservative forces. And they exist in several different forms: friction and drag, any pushing or pulling force, tension in a rope, or the normal force, which prevents objects from sliding through each other. Let's look at the total energy of a system and when the total energy is conserved. We know that there are two kinds of forces. Forces that can be associated with conservative work and forces that are associated with non-conservative work. As we can say that the net work done is the summation of work done by the conservative forces plus the work done by non-conservative forces. We know that the work done by conservative forces can be written as the negative change in the potential energy. And we know from the work-kinetic energy theorem that the net work done is equal to the change in the kinetic energy. We can combine these three statements to say that the negative change in potential energy plus the work done by non-conservative forces is equal to the change in kinetic energy. We can rearrange this system to say that the work done by non-conservative forces is equal to the change in kinetic energy plus the change in potential energy. We can then define the total energy as a summation of kinetic energy plus potential energy. And so therefore we can rewrite the above statement as a change in the total energy of a system is equal to the work done by non-conservative forces. If there happen to be no non-conservative forces acting on or by the system, then its internal total energy won't change over time. And this is a statement known as the conservation of energy. Here's what that looks like. If we have a system that is isolated from the environment, meaning there's no interaction with it, then there's no change in that system's total energy, or delta E equals 0. If, on the other hand, the system is not isolated, and something in the system does work on something in the environment, then the energy of the system will decrease. If, on the other hand, something in the environment does work on something in the system, then the energy in the system will increase. Let's look at two different methods of finding the landing speed of an object that has fallen. So here's a crystal that falls through a distance h. And in the first method, we'll find the landing speed using kinematics, which you should have already learned. So first, we'll identify that we'll take the downward direction to be positive. We'll note that the acceleration is just the acceleration due to gravity. The object is released from rest, so v sub 0 is 0, and the final velocity is just v. We can say that the object was released from the origin, so y equals 0, and it falls through a distance h, so y sub f equals h. Here are the two kinematic equations, which relate velocity and position to time. We can plug in the above values and then solve for the landing speed, which is v, which is equal to g times the time of flight. The time of flight can be found from the second equation, where the time of flight is the square root of 2 times the height divided by g, and then the landing speed is the square root of 2 times g times h, which is what we were looking for. Now, let's do the same problem, but this time using an energy analysis. We'll note the initial and final velocity again. We know that the change in the y-coordinate is h. We can calculate the change in the kinetic energy. Because it's released from rest, the change is just equal to the kinetic energy at the bottom, which is 1/2 mv squared. The change in the potential energy due to gravity is negative mgh. There are no non-conservative forces acting on the crystal, so W sub nc is equal to 0, and therefore the energy of the system is conserved. We can use the above values to say that 1/2 mv squared minus mgh is equal to 0, and use that to solve for v. And we'll get the same answer as on the previous slide, the square root of 2gh. One thing to note is that there's no way of getting the time of flight with this method, and that's usually the case with energy. Let's look at an example of drawing energy diagrams. Here, an object is thrown straight upward with the absence of any air resistance. And we'll look at 3 states. The first state is when the ball is initially launched, state A. In state B, the ball has reached the peak. And in state C, the ball has come halfway down. We're going to draw energy diagrams where the energy in each column varies from 0 to 100%. We want to find the kinetic energy, the potential energy, and the total energy. In state A, all of the object's energy is kinetic energy. So 100% is kinetic energy. And this is the beginning of the launch, so all of the energy is still present. And there's no potential energy because it's on the ground. In state B, the object has reached the peak, meaning it has no more speed to go upward. So the kinetic energy is 0. But it's at the peak, so the potential energy is at its maximum. And all of the energy is still there because there's no non-conservative forces acting on the system. So the total energy is also still at 100%. When the ball has come halfway back down, it's partially kinetic energy and partially potential energy. Because it's halfway down, the potential energy is only at half. Again, there are no non-conservative forces acting on the system, so the total energy is the same and it's still at 100%. And what's remaining is the kinetic energy. Let's look at another example, drawing energy diagrams. In this example, a block slides down a ramp with friction, bringing it to a stop at the bottom. We'll look at 3 states. In the first state, the block is initially released. In the second state, the block is halfway down. And in the final state, look at when the block has reached the bottom of the ramp. Just like before, we want to find how much kinetic, potential, and total energy are there, but because there's friction, some of the energy is lost. So we'll create a 4th column for lost energy. In state A, the block is initially moving and no energy has been lost yet. So all of the energy is present. Some of the energy is kinetic energy, and because it's above the ground, some of the energy is potential energy. We don't know how much kinetic energy is there because we don't have the numbers, but we can just make a guess and say it's somewhere around there. The rest must be potential energy. So the kinetic energy plus the potential energy must be the same height as the total energy. Instead of looking at the halfway point, let's look at when the block comes to a stop. When it's stopped, it's no longer moving, so the kinetic energy is 0. It's at the bottom, so the potential energy is 0. Because the kinetic and potential energy are 0, the total energy is also 0. And that means all of the energy that the block had in state A must have been lost. Now let's look at state B, the halfway point. Because this is the halfway point, the amount of potential energy is half of what it was in state A. So we'll just take the amount of potential energy and divide it by 2. Now the object is still moving, so it has some kinetic energy, but it's slowing down, so the amount of kinetic energy is less. Because we don't have the numbers, we don't know exactly how much, So we can just pick a value to make sure it's smaller than what it is in state A. We'll say it's something like this. And instead of putting it in the kinetic energy column, I'm going to put it on top of the potential energy. Now the height of the potential plus kinetic energy column is equal to the total energy. The amount of energy that is above the total energy up to the 100% mark, that is the amount of energy that was lost. That concludes today's lesson on working energy. Let's review the 4 key lessons that we learned. First is the definition of work. When a force displaces an object, that force does work. The work is calculated by finding the amount of force that is parallel to the displacement and then multiplying it by the amount of displacement. Then we saw the work-kinetic energy theorem. That is, the net force acting on an object does net work on that object. And the amount of work that is done is equal to the change in that object's kinetic energy. We saw that there are various forms of energy. There's kinetic energy, which is associated with the motion of an object. There's potential energy, which is energy stored in the configuration of a system. Then we saw energy conservation. We found that the change in the total energy of a system is equal to the amount of non-conservative work done on the system. If there's no work done on or by the system, then there's no change in the total energy of that system. Before I end today, I would like to leave you something to think about. In an isolated part of the universe, a piece of clay moving at constant speed collides with and sticks to another identical piece of clay. After the collision, the new combined piece of clay move in the same direction as the first piece. Find the kinetic energy of the system before and after the collision. Here's how to do that. First, I'll draw a diagram that shows the pre-collision and post-collision state. The mass of each object before the collision is m, and the combined mass after the collision is 2m. The speed of the first piece of mass moving is v sub 0. The other piece of mass is at rest. After the collision, the combined masses move with a speed v sub f. Because there are no external forces acting on the system, momentum is conserved. We can find the momentum by calculating mass times velocity for each piece, and then solve for the final velocity. We get v sub f equals 1/2 v sub 0. Then we can find the kinetic energy before and after the collision. We find that the kinetic energy before the collision is 1/2 m v sub 0 squared. And using the value for v sub f found using momentum, we find that kinetic energy after the collision is 1/4 m v sub 0 squared. We can then divide these two and then rearrange to find that the kinetic energy after the collision is equal to 1/2 of the kinetic energy before the collision. And so the question for you, if the final kinetic energy is only half of the initial kinetic energy, where did the other half go? And I'll give you a hint. It has nothing to do with heat, friction, light, sound, or any of those other kinds of things. So give it a thought. Appendix 1. Additional units of energy and power. A long time ago, physicists used to think of energy as being a particle. And when energy was transferred, that particle would move. Those particles were called calories. Later on, atomic physicists went looking for those calories, but they could never be found. And so physicists have changed the way they think about energy. So we no longer think of it as being a particle. However, the language of using calorie as a unit has still stuck with us to this day. And it's not very commonly used, but you'll sometimes see it in food or in older books. And 1 calorie is the amount of energy that is needed to heat 1 gram of water by 1 degree Celsius, which is equal to 4.184 joules exactly. Now, the food industry likes to use calories, but 1 calorie is too small, so they often work in units of 1,000 calories, or a kilocalorie for short, which is commonly used in Europe. Some authors will use a capital letter C to indicate this. Another unit of energy used for heat is the British thermal unit, which is approximately 1 kilojoule. And it's the amount of heat needed to heat 1 pound of water 1 degree Fahrenheit. Power is sometimes measured in units of horsepower, which a long time ago was a unit of measurement from actual horses. And it varies depending whether or not you're using imperial, metric, or even other variation forms. They're all approximately 740-ish watts. Appendix 2, example of a simple machine, Part 3, continued. In Part 3, I left you with 3 questions, and I'll answer them here. Why does the lever need to be rigid? If the lever is not rigid, some of the work done will go into deforming the lever. Why did the system need to be isolated for the previous analysis to be true? If the system is not isolated, some energy will enter or leave the system, which in turn changes the amount of work done. If the lever's length was fixed and F1 was constant, how could the system be modified to increase or decrease F2? To increase F2, the fulcrum should move closer to the right to decrease D2 and increase D1, then vice versa to decrease F2. Appendix 3, work done on a spring. In this slide, we would like to find how much work is needed to be done to compress a spring. When a spring is compressed, it will try to uncompress, and the amount of force it does that with is proportional to the distance by which the spring was compressed. The proportionality constant is called K, and it's known as the spring constant. Large values of K are for very stiff springs. L here is just the uncompressed length of the spring, so X minus L is delta X, the amount by which the spring was compressed. In order to do that, you have to push against the spring. And we know from Newton's third law that that will be equal in magnitude but opposite in sign of the spring's restoring force. We would like to find how much work is done by this. Now, as the spring is compressed, the force varies. It's no longer constant. So we can't just multiply the force of the spring multiplied by the displacement, because the force is varied. To find how much work is done, we can plot the force on the spring against its displacement. And this will be a line with a slope of K. Now what we can do is look at very small sections of the displacement. And these will just be rectangles. Now in each of these rectangles, the displacement is very small, so it can be approximately thought of as being constant. So to find the total work done, we just have to find the summation of the product of the force on the spring multiplied by that small amount of displacement for each of those rectangles. And then we take the limit as each of those rectangles becomes smaller and smaller. And this will just be the area of a triangle. The area of a triangle is 1/2 multiplied by the base of the triangle multiplied by the height of the triangle. The base here is just the total displacement, and the height is the maximum force on the spring, which is K delta X. Combining that, we get that the total work in order to compress a spring is 1/2 K delta X squared. Now, the work needed to do this did not depend on the path that we took. You could have done it slowly or fast. You could have gone in a little bit and then stopped and then gone in a little bit more. The only thing that matters is the total displacement. And so the work done on a spring will be conservative, and we can associate a potential energy with that. And the potential energy in the spring is just 1/2 K X squared.